Hello. Now, we will continue our discussion on the moment distribution method. Now, let's work on another example problem. This problem is actually very similar to the previous example problem that we worked on. The only difference is at the end, we don't have a fixed support, but a pin support. So here, another pin support and a fixed support. Same uniformly distributed load, 24 kilonewton meter. This distance is 8 meters. This one is 6 meters. So now we have a pin support here. Let's say at point C. This is point B, A, B, and C. Now our solution will start with the discretization, as we always do. Let's simplify the structure and decide how we want to analyze it. Now, in this structure, we have two members and three nodes. And the degrees of freedoms, I have rotation here, theta b. And if we use modified equation for this member, we know that we can eliminate the rotation at point C. In other words, I don't have to calculate the value of that rotation. This is our approach in slope deflection method. But let's again repeat that. So we did the discretization. We have 1 degree of freedom, rotation at B, meaning that we will do moment distribution at point B. So let's calculate the stiffness factors now. Stiffness factors. So I have two members. I am doing moment distribution at A, at B. So the stiffness factor for member AB, in order to determine that, this is what I'm saying. I am doing moment distribution at point B. So I'm looking at the far end condition. Is it free to rotate? The answer is no. So the stiffness factor will then be equal to 4EI over 8. Now, I ask the same question for member BC. I'm doing moment distribution at B, looking at the far end condition. Is it free to rotate? The answer is yes. So the stiffness factor for member BC is equal to 3EI over L, which is 6 for this case. So we have the stiffness factors. Now let's calculate the distribution factor for each point. So distribution factor AB is equal to 0. So let's remember what this 0 represents. When there is a moment at this point, at point A, this moment will be carried by the support. It will not be transferred to member AB. So this is what this 0 means. Now, distribution factor BA, meaning that I have a moment at B, what percentage of moment will be carried by member AB? So we do it by taking the ratio of the stiffness factor of member AB divided by the total stiffness factors at node B. We have two members joining to node B. Stiffness factor of AB is 4EI over 8 plus the stiffness factor of member BC, 3EI over 6, and that will be equal to 0.5. So half of the moment will be resisted by member AB. So the other half will be resisted by member BC. Now, let's also calculate the stiffness factor, the distribution factor CB. So let's figure out what we meant by that. When I apply a moment to node C, since I don't get any resistance from the support, all of this moment should be resisted by member BC. So if we write that in equation form, the stiffness factor of member BC is 3EI over 6 divided by 3EI over 6 plus the additional resistance to rotation at that node. So we don't get any resistance from the support, so I'll just write 0 here. So the distribution factor is equal to 1, meaning that whenever I have a moment at point C, it will be 100% resisted by member BC. So we calculated the stiffness factors also. Now let's figure out when no nodal deformations in the structure. What are my loads? Remember that we calculate this by calculating the fixed end moments. So no nodal deformations. Again, let's show the discrete version of the structure. Member AB, member BC, uniformly distributed load here. Now I'm showing fixed support here just to remind me that I don't have any deformations at the member ends. In this here member, I just showed the fixed here because the far end is free to rotate. We decided to use the modified equations. So that's the picture. Now let's calculate the moments for this given picture. So fixed end moment AB is 128. BA is again clockwise direction 128. And this moment I will be using WL square over 8, and this is 108 kilonewton meters. Now we have all the information that we need. Now I can start the moment distribution. So this is point A, point B, point C. So let's draw our table. Point A, B, and C. Let's write the distribution factors first. So if I have a moment at point A, it will all be carried by the support. Distribution factor is equal to 0. Distribution factor BA is equal to 0.5. Distribution factor BC is equal to 0.5. And this one is equal to 1. Now all nodes are clamped. So we are not allowing any, or in other words, all the values of all the degrees of freedoms are equal to 0. So basically I'm talking about this picture right now. No deformation, no nodal deformations. So this is, we get it by the fixed end moments. So I got 128 at point A minus 128 at point B and 108 again at B on the other side. So when there is no deformation, no nodal deformation, this is the picture that we see. And as you see, the structure is not in equilibrium. So node B should rotate in such a way that these two moments, 128 and 108, should balance each other. Now, when I look at this node, I see an unbalanced moment whose magnitude is minus 20. So you can consider this as an externally applied moment. It's an unbalanced moment. Now, half of it will be resisted by member AB, so resisting moment is 10, and the other half will be resisted by member BC. I'm saying half because the distribution factors are equal to 0.5. So this is the distributed moment when we remove the clamp at B. Now when I remove the clamp, there's a rotation, and due to that rotation, I got plus 10 at member AB and plus 10 at member BC. Now remember, we have a rotation, and due to that rotation, I will see carryover moment. So 5 will be go to the fixed side, fixed end. What about this part? Will there be any carryover moment? So let's discuss that. Now let's draw a simply supported beam, okay? And let's try to mimic what we see over here. So here I have a moment. Let's say that it's in this direction. Doesn't matter actually. A moment, okay? And due to that moment, we see a rotation, theta, and we see a deformed shape like that. But at this point, since this end is free to rotate, I don't have any moment. Moment is equal to 0, meaning that if I have a end that is free to rotate, my carryover factor is 0. Basically it tells me that no carryover moment. Okay? So no carry over. Now the structure is in equilibrium because this moment will be totally carried by support A, and I can calculate the final moments. So here I have 133, here I have minus 118, 118 and 0. So these are the final moments, and if I draw the free body diagram, this is what I see. So at point A, I have a counterclockwise moment. Magnitude is 133 kilonewton meters. At point B, I have a clockwise moment. Magnitude is 118. And again, at members BC, at B, I got a counterclockwise moment, whose magnitude is 118 kilonewton meters. So that concludes the solution of this example problem. Okay, now let's continue. Now I will be solving this time another problem. Again, it will be derived from the previous example problems, but this time I will add one more span to it. So basically in this structure we will be having 2 degrees of freedoms. So let's add one more span. So the first span is 8 meters. second one is 6, and the third one is 6, and we have the same uniformly distributed load on it, 24 kilonewton meters. Oops, sorry. Let's put the labels. Point A, point B, point C, and point T. So basically this is a 3-span continuous beam, and we want to analyze it by using the moment distribution method. Again, do the discretization. That's always the way we start. Point A, B, C, and D. Let's take a look at the degrees of freedoms now. So again, we have a rotation degrees of freedom theta B, rotational degrees of freedom here theta C, and if I use modified for member CD, then basically we have 2 degrees of freedom in this structure. So I have to do moment distribution at 2 different nodes. But in order for me to do the moment distribution, I have to calculate the distribution factors. So the starting point is the stiffness factors. So KAB, both sides are not free to rotate, so its stiffness factor is 4EI over 8. The second member KBC, now on one side I have member AB, so I cannot say that this point is free to rotate because I will get some resistance from member AB. And point C, it's not free to rotate because now I have an additional member here, member CD. It will give some resistance to rotation. So both sides are not free to rotate. So its stiffness factor then be equal to 4EI over 6. And KCD, let's check. This part is not free to rotate, but far end, no additional members here. I have a pin support here, so this member one end is free to rotate, so its stiffness factor will be equal to 3EI over 6. So we got 3 members and we determined the stiffness factors of all these 3 members. Now we can calculate the distribution factors. Let's start from node B. So distribution factor BA is equal to, I got 4EI over 8 is the distribution factor for member AB, divided by the total stiffness at B. 4EI over 8 comes from member AB, plus 4EI over 6 comes from member BC. So the distribution factor is equal to 0.428. Now distribution factor BC is equal to, I got 2 members connecting to node B. One of them carries almost 33% of it the moment, so the other one will carry 1 minus 0.428. That's equal to 0.572. In other words, 57% will be carried by member BC. Now distribution factor CB is equal to 4EI over 6 is the stiffness factor of member BC divided by the total stiffness 4EI over 6 plus 3EI over 6. So this will give me a distribution factor that's equal to 0.572, and the distribution factor CD will be then equal to 0.428. Now we know that this distribution factor for node A is equal to 0 and distribution factor DC is equal to 1. So I didn't write them one more time. So let's calculate no nodal deformation case, meaning that what is the picture when theta B and theta C is equal to 0. So again, I will be drawing the discrete version of the structure. So no zero rotation here. Theta B is equal to 0. So I'm just showing fixed end here. Theta B is equal to 0, fixed. Theta C is also equal to 0, fixed. And this is fixed. The far end is free to rotate. So that's the picture, and I have to calculate the end moments for this picture now. And this one is 128 kilonewton meters. 128 kilonewton meters. This one, WL square over 12, gives me 72 kilonewton meters. This one, 72 kilonewton meters, and that one is equal to 108 kilonewton meters. So this, remember that this will be our starting point in the moment distribution. Now I can start doing the moment distribution. So let's draw the table. Now this will take some time, so I will draw a long table. This is point A, point B, point C, and point D. Now let's write the distribution factors first. This is fixed support 0. Distribution factor BA is equal to 0.428. Now distribution factor BC is 0.572. CB again 0.572, 0.428, and this factor is equal to 1. So these are the distribution factors. Now let's write down the fixed end moments. So here I got 128 minus 128, 72 minus 72, 108. Okay, when all nodes are clamped, this is what I see. And as you see, the moments at node B and also the moments at node C are not in equilibrium. So we start from node B. Remember that all the nodes are clamped. Now I am releasing the clamp at B. So there will be rotation. The unbalanced moment will be equal to minus 656. Now I'm still clamping C. C is not rotating. I'm only allowing the rotation at B, and this rotation is caused by this unbalanced moment of 56 kilonewton meters. And 43% of this 56 will be resisted by member AB. So I'm multiplying 56 by 0.428. That will give me a moment that's equal to 23.97. And the rest will be resisted by member BC. So 56 times 0.572 is 32.03. And now node B is in equilibrium. So let's write it, distributed moment B. So we are allowing rotation at B. Carryover moment. Now since we have rotation at B, there will be carryover moment. And half of this moment will go to node A. So 11.93. Remember that C is still clamped. We are not allowing any rotation. So half of this moment should go to node C. 16.01. Now after that cycle, the node B is in equilibrium, but we still don't have any equilibrium at node C. So let's calculate the unbalanced moments. So these two moments are due to the applied loads, and 16 kilonewton meter is due to the rotation at B. So the total unbalanced moment, I just add all of them, is equal to 52.01. Now let's release the clamp at C. Now when I do that, the unbalanced moment is 52. 57% will be carried by member BC. So this is minus 29.75. And the rest will be carried by member CD. This is minus 22.25. Now, there's a rotation at C, right? Because of the unbalanced moment. And this rotation caused a moment at BC that's equal to minus 29.75 and minus 22.25 at member CD. Since there is a rotation at C, there will be carryover moments. So half will go to node B. So minus 14.87. And we don't have any carryover moment to node D because it's a pin support. So this is the carryover moment due to rotation at C. Now, as you see, C is now in equilibrium, but due to the carryover moment, this 14.87, this time node B is not in equilibrium. Now I'm clamping B and releasing, I'm clamping C and releasing B. Now B can rotate, distributed moment B, and due to that rotation, 14.87 times 0.428 gives me 6.36 and 8.51 here, and I will have carryover moments due to rotation at B. So half will go to node A, 3.18, and the other half will go to C, 4.25. Okay, after that cycle, B is in equilibrium. Now C is not in equilibrium because this time I have another unbalanced moment that's equal to 4.25. Let's continue with one more cycle. Clamp B, release C, and then unbalanced moment is 4.25. So because of that reason, I see 2.43 here and minus 1.82 here. This is the distributed moment C. Half will go to B, minus 1.21, and of course no carryover to D. So this is the carryover moment due to rotation at C. So if you continue like that for a couple of more cycles, you can obtain the final moments. The end moment, of course, there will be some unbalanced moment, but that would be a very small number. We can ignore that. And at the end of the day, the final moments are as follows: 143.42 minus 97.15, 97.15 minus 83.79, 83.79, and this one is 0. Remember that we determine, this is very badly written, let me rewrite that, 97.15. When do we stop? We do the distribution. We no longer do the carryover moment because all the nodes are in equilibrium, and then we add. We stop after we do the distribution, and we obtain the final moments. How do we obtain the final moments? Let's remember that for node A, 128 due to the applied moment when there is no deformation. 11.98 is due to the rotation at B, and 3.18 is due to the further rotation at B. We add them up, we obtain the final moment at point A. Let's take a look at this moment now, moment BA, minus 128 due to the fixed end moment, no rotation at B. We allow rotation at B, now we see 23.97. Again, there's an unbalanced moment, a carryover due to the rotation at C. We allow node B rotate further, and we obtain another moment, 6.36. We add this one, that one, and this moment, we obtain 97. So for all the cases, we add these numbers and obtain the final moments.